All right. So I prepared a very long, a rather long set of slides for this school. The first part has to do more about describing and understanding the atmospheric delays with which we have to deal with in space geodesy, and then the second part are some thoughts about the atmospheric ties. So in space geodesy, in geometric space geodesy, we're mainly concerned with 4 space geodetic systems. So in this picture, you can see the global navigation satellite system. On the left, you have the ground station network from one of the Cerebro 3, and on the left you have the tracks of the orbits of about 120 satellites for one day. Then we have the very long baseline interferometry technique. So with VLBI, we observe we have fewer stations, less than 50 active stations around the world right now, and we observe extragalactic radio sources, quasars. Then we have satellite laser ranging. Unlike GNSS and VLBI, this is an optical technique that operates mainly at 532 nanometers. There are about 35 stations. Here I plot the tracks of about 9 spherical satellites. And last but not least, we have the Doris system. It's French. There's an excellent ground network, again, around 50, 60 stations. And yeah, and here you see the tracks of the satellites that are tracked by the Doris system. So why are we in space geodesy? We're mainly interested in the estimation of position. Why is troposphere important? So we estimate northeast up component for the station position. We estimate clock. We estimate also, we have this zenith delay and gradients, and this is if you analyze GNSS data for, let's say, an hour, and you obtain the covariance matrix, and from this covariance matrix you obtain the correlation matrix, it looks like that. So what we see here is that there are some very important correlations between the non-hydrostatic delay, the zenith atmospheric delay, and then the clock and the height, the radial displacement. And also there are some significant correlations between the gradient north, gradient east, and the east and north station displacement component. So this is, I think, some motivation that tells us why there is this interplay between troposphere clocks and positioning in space geodesy. So so these are 4 techniques. We have 3 techniques operating in the microwave spectrum: GNSS, VLBI, and Doris. So lowest is Doris. Doris has 2 bands, 0.42. GNSS has 1.1, 1.5 gigahertz, and VLBI starts from 2 and goes up to 14 gigahertz for space geodesy. So SLR operates usually in the 532 nanometers, but there are some also infrared systems. So the signal propagation. What we want to know in space geodesy is the difference between this red line and the black line. The black line is here symbolizes the time it would take the signal to come from the satellite to the station if there was no atmosphere. So, but what happens in reality is that the signal that is emitted from the satellite is bent, travels along a bent path, and travels at a speed that is slightly smaller than the speed of light because of refraction. Now, this delay depends on the direction, the frequency, and of course the density of the medium. It matters the electron density that we have in the ionosphere, and also the pressure, temperature, humidity in the troposphere. If you write the equation, you can express it in terms of propagation delay and in terms of ray bending. So how much more time it takes to travel along the bent path, and what is the difference between traveling in a straight line as opposed to a bent path. So the ray bending is only important if you go to very low elevation angles. So at higher elevation angles, it's higher than 30 degrees or something, ray bending has almost a very small contribution, almost zero. So to do all that, we need to know the refractivity. And for the ionosphere, it is a function of the electron density and the magnetic field. And for the atmospheric component, it is a function of the pressure, water vapor pressure, so humidity, and temperature. So we said before that we have 3 techniques that operate in the microwave domain, GNSS, VLBI, and DORIS. And so these techniques, to calculate their refractivity, for these techniques, we need pressure, temperature, humidity. And for the optical refractivity, so SLR and also lunar laser ranging, in addition to pressure, temperature, humidity, we also need the frequency of the signal. So the delay is frequency dependent. And also in these equations for SLR, there is a small term that says that the hydrostatic delay for optical signals depends also on the concentration of carbon dioxide. However, this is a very small component. Now, we can decompose this, the refractivity, we can decompose it into 2 parts. The first is the hydrostatic part. And the hydrostatic part is something that is very predictable, right? And then we have the non-hydrostatic component. And the non-hydrostatic component is mainly due to the water vapor in the atmosphere. And this is not very predictable. And this we usually have to estimate employing the space geodetic measurements. Now, let's discuss for a second about the ionospheric effects. So for microwaves, the ionosphere is a dispersive medium, which means that if you have observations at 2 or more frequencies, you can mitigate first-order ionospheric effects, and this is known for many years, and this is done. And this is why in GNSS and VLBI and DORIS, we always observe at least 2 frequencies. There are many ways to do it. One of the ways is to apply something like that. And if you do the error propagation in this equation, you will see that you sacrifice reducing or almost eliminating a systematic effect for noise. So these P3 and L3 observations, they will have a higher uncertainty compared to the single frequency observations. For VLBI, something similar happens, and so for GNSS, VLBI, and DORIS, there are also the so-called higher order terms, but they are again a function of frequency, and the higher the frequency, the smaller these terms. So for VLBI, for example, these higher order terms are, I think that they're not applied because the contribution is extremely tiny. Yeah, so the movie I created here is based on global ionospheric maps from processing with GPX, and it shows how the vertical total electron density changes throughout the day. And you see that it closely follows the movement of the sun. And if you take a time series either from VLBI, as you can see in the top panel, or GNSS in the lower panel, this vertical total electron content, it has some annual variability, and it also has now to understand and better do better job in terms of atmospheric delay calculations for space geodesy. One of the tools that we use is ray tracing. So ray tracing is extremely important, and the way it works is that if you know where your station is and where the satellite is, you also in between. And then what you do with ray tracing is that you find the path that the signal will follow to come from the satellite to the station. So after you find this path, then you do a simple numerical integration, and you have calculated the delay. The state of the art, the accuracy of this ray traced delays, atmospheric delays that we can calculate based on state-of-the-art models. They have an accuracy about 1 centimeter in the zenith, and if you look at lower elevation angles, then it gets the uncertainty grows. Now, the problem with this ray tracing is that while it's very accurate, it's also extremely expensive. So if you want to use a meso beta scale model, so like ERA5, which has a temporal resolution of 1 hour, and if you use the model level data, you have something like 137 levels, 30 kilometers. It costs about 18 terabytes per year to just from a disk storage viewpoint. Also, this is a very intense procedure to do the ray tracing, and this is why we use a parameterized version. And you can parameterize the delay as a function of direction, and then there are some empirical models for time, for example, that you don't need to calculate the delay every hour, but you have annual, semi-annual, diurnal, semi-diurnal harmonics to describe the delay. The most common parameterization is the following. So on the left, you have the atmospheric delay as a function of elevation and azimuth at a certain epoch, and it is decomposed into the so-called symmetric delay. You have with this MF, this is the mapping factor, and here you have a zenith delay. So the first part with the subscript H is the hydrostatic. This is delay because of dry gases, and this is something very predictable, right? We can know with very good accuracy in advance. Then the second part, the second addend, the NH is non-hydrostatic, and this is mainly due to water vapor. And our numerical weather models cannot describe this very accurately. In addition to the symmetric delay, we have the asymmetric delay. You see in the first line, everything is a function of elevation angle, epsilon. And in the second line, we see that we have the azimuth that appears in the equation as well. And the symmetric delay, we have these so-called gradients, okay? And so we said that the gradients and the non-hydrostatic delay, which is mainly due to water vapor, they are not very accurately predicted by weather models, and this is why we estimate them based on the space geodetic observations themselves. So the parameterization is extremely important. So please try to follow me in this graph. This is a snapshot of the atmospheric delay at one random station at one epoch. The horizontal axis is the azimuth from 1 to 360 degrees, from 0 to 360 degrees, and then the vertical axis is the slant delay at an elevation, at a very low elevation angle. So if you choose to use only the symmetric delay, then your model is a straight line. However, you can see that this bold, this strong line, it shows that the delay is not constant as a function of azimuth, but changes very much. And if you look to the units on the right hand side, you can see that the variation reaches almost 1 meter. And given that our observations in GNSS and VLBI, they have an uncertainty in the order of millimeters, then this is an error that we cannot afford to have in our analysis. And this is why we should really take into account the gradients in modeling the atmospheric delay. So if later on, we will talk about differences between GNSS and SLR, and it starts from again from the modeling viewpoint. We have the north-south gradient. For microwaves, it looks like that, and then for optical, so for lasers, for SLR, at a certain epoch, it looks like that. So what we can see is that on the southern hemisphere, the north-south gradient is mostly positive, and in the northern hemisphere, it's mostly negative. And this is why because of the flatness of the Earth. That's why. And that the fact that the atmosphere, the depth of the troposphere is bigger at the equator compared to the depth of the atmosphere at the poles. Then we also have the east-west component, which is it is less systematic. We said before that these atmospheric delays, they can be quite uncertain. The graph here illustrates the zenith-wet delay from era 5, so one epoch minus the long-term average. So you see that the signal can change, let's say plus minus more than 20 centimeters. And then we have also some other components of the delay. So, but they are not. We have the hydrometeors, and then we have the gradient amplitude. So if you take two state-of-the-art models, that's what I did here. I took R5 and also ICON. ICON is a model. It has a spatial resolution of 13 kilometers global, very accurate, state-of-the-art. And if you compare R5 with ICON, we see here that the differences in terms of the zenith delay are larger than several centimeters. So we cannot simply take the zenith wet delay from a weather model and use it in our analysis, because simply which model to use. So they are not accurate enough in this regard. We need to estimate the atmospheric delays and gradients, the zenith delays and the gradients. We need to estimate them based on the spatial data. Now, for I took here 2 weeks of data, and here I plot the so-called zenith total delay. In the black line, you see at the station in Germany, what is the zenith delay for GNSS station, and then for exactly the same location, what is the zenith delay if we have an SLR station. So we notice two things from here. The first is that for SLR, so the optical delay, it is much smoother. That's first, because the laser is not as sensitive to water vapor as microwaves. First, more smooth, and then second, at this frequency, 532 nanometers, the green laser, the zenith delay is slightly larger. That's the first. Second, for the gradients, we see that the GNSS gradients, they are, let's say, a quite noisy time series, but the gradients from SLR, they are also very smooth. And this is again due to the absence of water vapor. This is here the west coast of Australia, and here there is a magenta dot for a station called Yarragadee. So what I did here is I did ray tracing for a long period of time, and then I calculated the gradient amplitude here at this station, and then I calculated the gradient amplitude at all the pixels that you see within this picture. After I did this, I took the time series at Yarragadee and the time series for the other pixels and calculated the correlation coefficient. So you can see that the closer somebody is at Yarragadee, the higher the correlation, right? And this is for microwave gradients. Now, if we change the frequency and we switch to the laser, we see that for optical frequencies, so for the lasers, the signal is spatially more coherent. So for microwave, it decorrelates very fast. For optical, it does not change very much as a function of distance. Now, we will talk about atmospheric ties in some minutes. So we have the atmospheric delay can be parameterized as a function of height. So what happens if what happens to the atmospheric delay if we go 100 meters higher? So for the hydrostatic component, this is what we can predict very well. More or less, if we go 100 meters higher, the delay will decrease by almost 3 centimeters. Why is that? Because the signal travels to an atmosphere that is less deep, 100 meters less deep. Then for the non-hydrostatic component, again, if we go 100 meters up, then the non-hydrostatic delay will also be smaller by 3 millimeters. And so I also did this exercise for the gradients. We see that the gradients, they also are smaller. However, they are not, let's say, significantly smaller. Now, so the space geodetic techniques that we use in geodesy, they observe at different frequencies. And when we calculate the atmospheric delays, the ionosphere is usually not considered. However, although ionosphere does not affect the tropospheric delay directly, it affects the ray path. So by changing the ray path, it indirectly affects the tropospheric delay because we need to integrate at a different path. So VLBI, as we said, has two frequencies. This is the legacy system, 2 and 2.3 and 84.4 gigahertz. This is the highest frequency, 8.4 gigahertz. You see that if you take into account the atmosphere in the modeling or not, then the differences are very small. So 0.01 millimeters, this is very tiny. However, when we go to 2 gigahertz, we see that the difference is again sub-millimeter level. So for GNSS, it can exceed the millimeter level in some cases. And the third a microwave system for geometric space geodesy, DORIS, we see that the difference can be quite large. So DORIS, the lowest frequency for DORIS is 0.4 gigahertz. And we see that if you don't take into account the ionosphere during modeling, you can have an error at the several centimeters level. Another issue when modeling the atmospheric delay using numerical weather model data is the orbital altitude. So the closer a station, the smaller the distance between the station and the satellite, the larger the bending. So for VLBI, the distance is infinity, billions of light years away, and for GNSS, so the difference between GNSS and VLBI is very small. So at an elevation angle of 7 degrees, it is a sub-millimeter level, right? But when we compare the delay between DORIS and VLBI, we see that the difference can be quite large. And this is why the satellites that are used during DORIS data analysis, they have an orbital altitude between 7 and it's always below 2,000 kilometers. So the lower the altitude, the higher the higher the slant delay. Another example that I put here, so if we want to track the GRACE follow-on satellite mission using satellite laser ranging, there are currently two mismodeling shortcomings. One is that the orbital altitude is not taken into account. So this will cause the atmospheric model that is used for SLR to be biased by almost 1 millimeter. So all the range is biased by 1 millimeter. And then the second is that although laser observations are affected by gradients, there is no modeling, so they're usually not modeled a priori, and they are also not solved during the processing. And this causes that the slant delays, they can be wrong by several centimeters if your station is let's say is not in the equator, and SLR has no stations within the equatorial belt. Now a few words about now we know what can be estimated with space geodesy. We know also some details about differences between microwave and optical delays. So how can all that be used? So there is this technique called radio occultation. So, and this is this red line here. And with this, you can derive profiles for example, humidity, temperature, and this is very important information that ends up into numerical weather models, and is since decades is a very important observation. Then something else that you can do is you analyzing GNSS data, you have to estimate the zenith delays and the gradients. Why? Because the weather models are not accurate enough, so we cannot fix them to some a priori values. And then we can use these zenith delay and gradient estimates to improve the numerical weather models by a process called data simulation. Another thing that we can do is we can compose a very long time series. So from this zenith delays, we can eventually calculate the integrated water vapor and calculate integrated water vapor trends. Now, these are very important because water vapor correlates with temperature. So an increase into water vapor is associated with an increase in temperature. So if we want to be able to better probe global warming, this is a very good tool. And last but not least is reflectometry. And with reflectometry, we can deduce the ocean surface, the roughness, and from this we can calculate the wind speed, and we can also so for stations that are let's say on soil or on land, we can calculate soil moisture in the immediate vicinity of the station. So a colleague from GFZ published an article recently. And this article is about the simulation of GNSS delay. So if you put just one observation, one zenith delay observation and one gradient observation in the numerical weather model, you see the impact it has. So this is a map of Germany. So just for an observation, you see how much impact it has, the zenith delay on the right and the gradient on the left. And then here in these graphs, you see on the vertical axis you have the height, and then on the horizontal axis you have the latitude, and you can see the extent to which assimilating either one ZTD or one gradient measurement with a very generous uncertainty affects the water vapor mixing ratio field. So nothing will happen after 6 or 7 kilometers if you put just one observation. Yeah, so so far we discussed about we said why studying the atmospheric delay is very relevant for space geodesy, because there is the correlation between the delay, the position, and the clock. Numerical weather models, we established that they are indispensable for the reduction of the space geodetic data, but they are not accurate enough, and that's why we need to estimate zenith delays and gradients in while we're processing GNSS VLBI and SLR data. We said that the optical delays, they are different than the microwave delays. They are smoother both in space and in time, and that the atmospheric delay coefficients, they decrease with altitude because the depth of the atmosphere is the signal simply has to travel less troposphere. Yeah, the GNSS derived atmospheric delays, what we do during the geodetic processing can be used, this byproduct can be used to improve weather forecast, and it is done by some weather services. Yeah, we have together with my colleague Florian and some other colleagues from GFZ, we published recently a software that you can download from GitLab, and you can have there are examples, there are data associated with it, and you can do your own ray tracing and calculate figures like the one that I have presented by yourself. It's very easy. There is a README file, and yeah, so feel free to use it. And now a few words about atmospheric ties. I'm going to start with VLBI. So in VLBI, very long baseline interferometry, we said that we have some station on Earth, we observe extragalactic radio sources, and we want to estimate parameters. what do we estimate? So our normal equation will be populated by a block that has station coordinates, another block that has the right ascension and declination, so the coordinates of these extragalactic radio sources. Then we have Earth orientation parameters, so polar motion, UT1 minus UTC, length of day, precession notation, celestial pole offsets. Then we have this tropospheric delays, what we discussed before, so zenith delays and gradients. We have clock parameters, so VLBI stations are equipped with active hydrogen masers. They have a precision of about 10 in the minus 15. And we need, during the processing, to estimate some functions to describe the behavior of these frequency standards. And there are some other systematic effects that we also need to take into account when we are analyzing VLBI data. So our normal equation matrix has these blocks, and some of these parameters, they are interesting for other techniques and can be derived by other techniques, such as the station coordinates, the Earth orientation parameters, and the tropospheric delays. So if the parameters are not identical, then we need to have these so-called tie vectors. So we have, first of all, the local ties. So when we're going to combine station coordinates, when we combine Earth orientation parameter, we have the global ties. Here, the vector is implicitly 0 because the same Earth rotation parameters that we estimate using VLBI data are the same Earth orientation parameters we expect to estimate using SLR or GNSS or DORIS. And so we can do the same thing with troposphere, of course, taking into account the things like the height difference between the stations. We can combine clocks. So there are quite a few stations where the GNSS station is connected to the hydrogen maser of the VLBI station. So in principle, the clock you estimate in VLBI and the clock you estimate in GNSS during PPP should give you the same result. So for the state of the art says that the combination, the inter-technique combination should be done using local ties and global ties, and there are some experimental combinations using tropospheric ties, clock ties, and also satellite ties. So if you observe satellites, which we currently do not do with VLBI, but will do with the Genesis mission, which will be launched by ESA in a couple of years. What are these ties now? The definition, let's say, how I understand ties are that they are the expected differences in the parameters that we mentioned. They need to be external, and they need to be more accurate than what we can get from the space-geodetic techniques. Why do we need them? Because they facilitate the combination of the techniques, and that way we can exploit the strength and mitigate the weaknesses from the different techniques. Then we can do datum transfer. For example, VLBI does not observe satellites, so it does not know where the center of mass of the Earth is. But when we combine VLBI with SLR, SLR observes low Earth orbit, observes satellites that orbit around the center of mass of the Earth. So when we combine VLBI with SLR, this information is transferred from SLR to VLBI. And then, since we can estimate the same things using different independent observing systems, we can detect technique-specific issues. On the right here, you can see some sky plots I created quite some time ago, and they illustrate how the targets appear from the GNSS viewpoint, VLBI, SLR, and DORIS. And you see that, for example, in techniques like DORIS and VLBI, the observation is relatively poorer compared to GNSS. So if you want to have a good tropospheric delay estimation, VLBI and DORIS will benefit from a combination with GNSS. So we said that we need this external information. We get this from a local service for the local ties. For the atmospheric ties, we get this information from usually from numerical weather models. For clock ties, there are systems in place in currently very few stations that the cable delays can be measured exactly. And for satellite ties, well, it's like a local survey, but you have to do it before the satellite is launched into orbit, because after that, there's not much you can do. Now, there are some discrepancies between what this external measurement gives us and what we can measure with the spatial-theoretic techniques. And so this is, in many cases, due to inconsistency in modeling and parameterization. There are some undetected systematic errors in the individual techniques, or there is some error during the measurement of the local ties. So in many of these systems, there is no single point that you can track and say this is at the center of the VLBI or the SLR system. It's many times it's an intersection of axes, which is no material point. For example, here, the graph in the graph here, you see on the horizontal axis the time, on the vertical axis you see the zenith delay differences between two stations. So I have already applied the expected atmospheric delay using R5 data. So if there was an agreement between the geodetic measurements and the weather model, there should be just some noise around zero. But this is not the case. What you see here is that there are biases, and these biases, they vary as a function of time. So this pair is something that should be revisited. What do we do when we detect such tie discrepancies? We can choose. If we have time in our hands, we can improve the modeling, parameterization, and the consistency of the techniques. We can. We can do some more measurements. This is for example, for the local ties, and if we don't want to do some improvements or do some measurements again, then we can simply downweight the local ties that do not agree with the results. We have already discussed this. So this is the covariance matrix. There are high correlations between displacement, zenith delay, and clock. That's why we are so much concerned with the modeling of the atmosphere. And these so-called atmospheric ties have been successfully applied in GNSS and the VLBI combination for many years. There are many papers about that. Many people have done it. And so we have a project where we do combination, not at the normal equation level, but at the observation equation level. So we have software that is able to do VLBI GNSS SLR combination. And so this is an example. On the vertical axis, you see the weighted root mean square error of position time series during a 2-week period. And what you can see here is that, for example, in green, you have the WRMS of the VLBI only solution, and then in blue you have the solution, the combined solution, GNSS VLBI, where local ties, global ties, and atmospheric ties are combined. So local ties, position; global tie, Earth orientation parameters, polar motion, length of day, etc. Atmospheric ties, zenith delays, and gradients. And you see here that the RMS improves by more than 10% in the north and east component, and close to 40% in the up component. Now, atmospheric ties in practice. What are these atmospheric ties? They are, in essence, stochastic equivalence constraints. So the parameters we're concerned are the zenith delays and the gradients. And so, for example, what we constrain is the difference. We say that the difference between, for example, VLBI and GNSS zenith delay at Vecel should be the same as the expected difference from R5 plus minus an uncertainty. So when we apply atmospheric ties, we need to make some decisions. So first of all, where do we get our atmospheric ties? Do we take them from a numerical weather model? Which one? Then second is, do we apply bias correction? So some GNSS stations are equipped with a a protective dome, a radome, and this has some. It causes a bias in the delays. So do we empirically remove this? Do we leave it in? What do we do? Then the atmospheric delay changes within a couple of minutes, but the difference between the atmospheric delays of stations that are nearby does not change as rapidly as a function of time. So do we apply something? Do we apply a constraint every hour, or do we just have a time invariant constant? Also, what uncertainty do we apply to this pseudo-stochastic observation? Yeah, before I continue, I would like to ask the organizers, how are we doing on time?
In fact, we are 6 minutes late, so I don't know how much time do you need.
Yeah, I think I will. I would like to take questions now. Because later on it gets more detailed, and so I think that all the important information about atmospheric delay modeling and what is going on with the combination and the ties has already been described. So I'm happy to get questions if there's time. If not,
Kyriakos,
yeah.
If you need, maybe 10 minutes more.
I'd rather have questions, because then it's what I have later on is an example from a study, and it's quite detailed. And
continue with your presentation. Don't worry.
All right. Okay. Thank you. Okay. So we did a couple of years ago. We did a study. And in this study, we wanted to combine GNSS, VLBI, and SLR data. So, we have the networks are very different. So for GNSS, we have almost 250 stations globally distributed. For VLBI, we had only less than 20, and for SLR, we had less than 30 points on the planet. This is for a 2-week period. So the way to do it usually is you say that the Earth orientation parameters between these 3 techniques, they are equal, and then you also combine with the so-called local ties. So local ties, it means that next to a VLBI station, in a distance of 50, 100, 200 meters, there is an SLR station or a GNSS station, and the difference between the distance is very accurately measured by a surveyor. So we see that, for example, for GNSS, from the 244 stations, we have local ties for less than 10% of the network, right? So very few. So I think this graph here on the right might be quite interesting to understand a little bit what's going on when we combine data from different observing systems. So there are 3 columns: GNSS, VLBI, SLR. The orange is number of observations. The purple is the number of parameters that are estimated during the processing. And then the y-axis is just number, and the scale is logarithmic. What you can see here is that the difference from SLR to VLBI and from VLBI to GNSS is more than 1 order of magnitude. So this should somehow be taken into account, the combination, by appropriate weighting. So how the combination is done, we start from the VLBI group delays. For VLBI, then we have GNSS and SLR. So for SLR, we analyze data for Lagios 1 and Lagios 2 only. Then we do the single technique analysis, and so for VLBI, we have station coordinates, radio ascension, declination, Earth orientation parameters, and atmospheric delays. So as we said before. And for GNSS, we have station coordinates, Earth rotation, zenith delays and gradients. And for SLR, we have station coordinates, range biases. This is an SLR station and satellite specific instrumental effect. So it's a fudge parameter that has to be estimated. And yeah, also polar motion, length of day, and zenith delays. Then we have the single technique solution, and then we take these three solutions and we get the combined solution with local, global, and atmospheric ties. So for the local ties, in total there were 36 vectors, and so local ties is station coordinates, global ties is Earth rotation parameters, atmospheric ties is zenith delays and gradients. And so in this study we chose to there were two approaches, and in one approach we constrain the difference between the delays at collocated stations. So we say the difference between, for example, GNSS and VLBI should, this is the measured difference, should equal the difference, the expected difference that we get from a weather model. And then, as we said before, we need to decide what uncertainty to put on this pseudo observation equation. And we had let's say 4 choices from 1 millimeter to 1 centimeter. And then we did an experiment to the scaling approach. Instead of constraining the differences, to constrain the ratios. We did many solutions. We have a reference solution. This is the standard, what is done usually. So local and global ties, so positions, station positions, and Earth orientation parameters. Then we have the scaling approach, and then we have the difference approach. There are lots of results here, but I would like to let's say skip some, if I may, and go directly to the summary and the conclusions. Time has passed. So when we combine GNSS, VLBI, and SLR, the normal equation, we can use atmospheric ties in addition to local and global ties. We see that the station coordinate and baseline length precision gets improved if we have tight atmospheric ties. So tight atmospheric ties was 1 millimeter. The local tie discrepancies improve if we have loose atmospheric ties. The results, the rest of the results are, let's say, rather expected. So in principle, if you impose loose atmospheric ties, it means that the influence of the atmospheric ties on your solution is not very big. However, in our consideration here, we used uniform weighting for the ties, and this is probably not very correct. Why? Because we found some biases, and we did not eliminate them. So, for example, for the stations that had biases, we either should have corrected them or downweighted these observations, and this would benefit the combined solution. And if one wants to repeat this line of work, currently it is impossible, because there exists no SINEX file from VLBI, GNSS, and SLR that contains these three sets of parameters that we combined here, which is the station positions, Earth orientation parameters, and atmospheric delays. What you usually find in these SINEX files are Earth rotation parameters and station positions. Currently, to my knowledge, there are no SINEX files that contain atmospheric delays. And the important thing is not the atmospheric delays themselves, but the covariance matrix between the atmospheric delays and the station positions. This is very important. Yeah, I think that's all. That's more or less I have for now. We have a project on the topic of combination of space geodetic techniques with atmospheric and clock ties. And yeah, we're busy at work to do this at the observation equation level. And yeah, if you're interested in the topic, yeah, get in touch. Thank you.
Thank you very much for your presentation. It was a pleasure for our community to take you in our school. There is one question. There were two, but I answered one about the ERA 5 model. So the question is Bruno Kimusleiri. Please, some lights on the impact of a mapping function in the tropospheric computations?
Yeah, so yeah, let me go to slide. Yeah. Let me go to an appropriate slide. Yeah, so the mapping function that the colleague refers to is this guy here. This is for the hydrostatic component, and then this is for the wet or non-hydrostatic component. So this mapping function, the state of the art says that you do. So let's say that you have a station of interest. What you do is you do ray tracing at 10 different elevation angles, starting from 3 degrees up to 90 degrees. And you do this for many azimuths. So you start looking at the north, and then you turn, you go to, for example, 30 degrees, 60 degrees, 90 degrees, blah, blah, 270, 300 degrees. So you have now all these ray traced delays. And so when you look at the zenith, the delay should be about 2, if you're at sea level, 2.3 meters. And if you look to the horizon, it can be close to 30 meters. So this mapping function is a quick way to describe how the zenith delay increases as a function of elevation angle. Now, this delay, this function, this is the mapping function. It depends mainly on the weather model data that you used. So if I calculate one with ERA 5 or with MERA 2 or another model, the mapping function will be different. There have been many papers since, starting since 20 years ago, comparing the impact of different mapping functions. In principle, I think the case is that if your model is more state of the art, if it has higher spatial and temporal resolution, then the more accurate is the mapping function that you're using. So that's one thing. So if you can, you should, in deriving the mapping function, use a as high resolution model as possible. One, and two is that there are two, let's say, schools of this mapping function. One is you get coefficients for every epoch. From TU Vienna, for example, you have coefficients every 6 hours. This is one approach. And then the other approach is you don't download data every 6 hours. You simply download some coefficients, and you can approximate the time series of this mapping function as a function. So you have some seasonal signal, so annual, semi-annual, diurnal, semi-diurnal, And yeah, so the second, so this approach with the empirical approach with the coefficients, it is of course cheaper. If you are a user and you want to apply, you don't need to download stuff every day 4 times a day. You just download the coefficients and you have them there forever. But of course, this comes at a cost, and the cost is reduced accuracy in the atmospheric delays you derive, and also the station coordinate positions. So the worse, if you do, the better atmospheric delay modeling you do, the better station coordinates you have. So the station coordinates and the atmospheric delays, they're in the same adjustment. So if there is lots of error in the atmospheric delays, it somehow propagates into the station positions as well. So yeah, I hope this is remotely helpful. Then there is also another question. Aside from the needs, so first of all, is this covered? Should we move to the next one? Okay, so aside from the need for SINEX files containing atmospheric parameters, what do you think should be done, or what infrastructure is necessary to implement to improve or increase data to determine atmospheric ties? Well, for atmospheric ties, so yeah, I mean the main component in atmospheric ties is the height difference. So yeah, using simply the hydrostatic, assuming the atmosphere is in hydrostatic equilibrium, and calculating the zenith delay difference based on that, in most cases you are not very wrong. Otherwise, best is of course if you download the weather model data, calculate the delays at exactly your locations, and then calculate the differences. This is of course the best. But if this is not possible because of technical difficulties, I think there are institutes. So Vienna provides grids of zenith delays, and you can do this from there. However, yeah, to my recollection, these grids are quite coarse. So I think there is a version of 1 degree and then another version of 2 times 2.5 degrees. So 1 degree is about 100 kilometers at mid latitudes. So, and then the collocations are maybe 50 meters away or 100 meters away. So yeah, I'm not sure how well this can be captured.
Thank